Hello everyone. A very good afternoon. So we'll begin with the webcast. So as you can see, you can ask your doubts that you have during the presentation by this chat window. Okay, and those of you who have a very slow internet connection, you can dial these numbers followed by these pins. I'll just repeat the numbers. The numbers for people who are attending in India is 1800-425-4061. Yeah, I'll just repeat that. 1800-425-4061. And you have to type the PIN, which is 507248 hash. That is 507248 hash. And for the viewers, the attendees outside India, the number is 9144-2370-2370. And the pin is 507248 hash, the same. Okay, so let's move forward. Okay, the topic of today's presentation is frequency domain measurements in audio applications using, of course, LabVIEW. My name is Amit Yadav. I'm an application engineer at National Instruments, and I have a team of consultants, technical consultants, who will be answering your queries. So let's move ahead. Okay, so the webcast, those who attended the webcast last time, it was related to acquiring data into LabVIEW. Okay, so the sound palette was explored in details. All the functions related to inputting sound audio signals into LabVIEW, and if you want to output audio signals using LabVIEW, how you can do that we saw. But that is just a very small part. But generally what happens is once you have acquired the data, you would like to do some processing, right? So today we'll be covering that, keeping audio applications in mind. Okay, so the first thing that arises is, why do we need frequency domain analysis? So those of you have observed, when you acquire a signal using the sound palette, the signal is acquired is time domain signal, right? So if you see the x-axis, that is time. So what information can you acquire using the signal? One very prominent is definitely amplitude, right? But the frequency of the signal is not very apparent. So let's say if we acquire a sine wave, right? So I can definitely find out from the time domain signal what's the amplitude. But it's not very apparent in the case of frequency. So there are a lot of applications which require us to have the frequency domain signal. So we'll be seeing how we can convert this time domain signal to the frequency domain signal using LabVIEW. That is first thing. And then what all we can do using the frequency domain signal. What all analysis that we can perform in the frequency domain. So we'll study this, keeping audio applications in mind. I have a demo also towards the end, which is related to one of the audio applications. All right, so let's move forward. So first, let's see what's a frequency domain analysis. Okay, we've seen why is it important. Now let's see what exactly is it. So as I talked about a time domain and a signal which has the x-axis is time. Okay, so in the frequency domain you have frequencies on the x-axis, and on the y-axis it could be either the amplitude or the power contained in each frequency. So and the general term for converting a time domain signal into a frequency domain signal is transform. So there are a lot of transforms. For example, there is one very popular transform called fast Fourier transform. Okay, which is very widely used in DSP applications. So we'll just study this in brief, which will help you to understand and appreciate the rest of the application better. All right, so let's look at some examples. Okay, so as you see on the screen, if you have a sine wave, so let's talk about a DC wave first. Let's say you have a DC wave. A DC wave is basically has zero frequency. So if I do a FFT of a DC wave, the graph which you see on the right side, right, as it has a frequency of 0. So some amplitude on the 0 frequency. So let's say I have a sine wave of a particular frequency. Let's, for example, 10 Hertz. So I'll have a different FFT graph for that, and so on. So these are very simple sine waves. Now let's look at more complicated wave which represents the signals in real world. So let's say you have a square wave. Now if you actually try to do an FFT for a square wave, you will find out that it consists of a lot of frequencies. Okay, so a very important concept that the people who are familiar with EC background who are familiar, and those who are not. So the concept is that any wave, any signal can be written as a summation of sines and cosines, right? So which basically means that I can break down any signal in terms of sines and cosines. So the graph that you see is, let's say if you have a square wave, you can break down into all these frequencies. One more concept that this slide depicts is that every signal has a fundamental frequency and it has something called harmonics. Okay, so the fundamental frequency, so let's say you have a square wave of frequency 100 Hertz. So that is the fundamental frequency, but there are a lot of harmonics associated with it. So harmonics are basically multiples of the fundamental frequency. So in the example that I gave, if I have a square wave of 100 Hertz, I'll have harmonics of frequency 2f, that is 200, 300 Hertz, 400, and so on. Right? So accordingly they're named as first, second harmonic, third harmonic, and so on. So if you actually plug something on your guitar, let's say, a string, an open string on your guitar, so a lot of, it's not a pure sine wave which is generated. Okay, along with it, a lot of harmonics are also generated. So this, I just told you because we'll be seeing these in detail later, as in how we can get the harmonics information from a signal using LabVIEW VIs. So let's move forward. Okay, so this is what we are going to study, these special VIs that are frequency domain measurement VIs. So we have 4 VIs in this palette. You can find this palette in the Signal Express palette. Then if you go to analysis and frequency domain, I'll show you a live demo of that. So what do these VIs do? So the input to all these VIs is a time domain signal, and the output depends on what the VI is supposed to do. So definitely all of these are doing frequency domain transformations, and depending upon the functionality of the VI, they do some frequency domain analysis. Okay, so let's look at these VIs in detail. So the first one is tone measurement. Okay, so this tone extraction VI, tone measurement, what it does is, if you give an input signal, it can detect the signal, it can detect the amplitude and of the highest frequency and the phase also of that. So if I give a time domain signal, if I give a sine wave of 100 Hertz, the output of detected frequency would be 100 Hertz, and the amplitude would be the amplitude of the corresponding 100 Hertz frequency. Fine. Now, people who are familiar with EC background would be familiar with this term. It's called frequency response. So basically, if you have any system, okay, for those who are not familiar, let's consider it's a black box. If you give some input, let's say X, which is called a stimulus, and if you give some response, let's say Y, so the system is supposed to have a transfer function, which is Y by X, right? How do you get something which when you pass X, it goes through the black box and gives you Y. So that black box is doing something to X to transform into Y. So that we call the transfer function of the system. So this VI that you have, if you give a stimulus and a response signals, it can tell you what was the transfer function of the system. Fine, let's move forward. The third one is power spectrum. As the name suggests, it calculates the power spectrum and it calculates the power spectral density of the input signal. Okay, so what basically it means is in each particular frequency, how much power is contained, okay, which is proportional to amplitude square. So that it will output. So the output of this is a graph which shows you how much power is present at a particular frequency. The last express VI that we're going to see today is a distortion measurement VI. Okay, so there are a lot of concepts in this. Let's look at this. So as in the previous slides, I talked about harmonics of a fundamental frequency, right? So this VI basically deals with that. If you give an input signal, input time domain signal, this VI will convert into a frequency domain signal, and then we'll calculate various parameters which are related to harmonics. One of those parameters is definitely a fundamental frequency that you can find out. Apart from that, it calculates THD, which stands for total harmonic distortion, okay, in percentage. So which basically means, let's say the power of the harmonics is P harmonic, and the total power is P total. So it's telling you how much is this ratio of P harmonics by P total. Okay, and there is one also very important term which is synad. So what this basically means is, so if you must be aware of signal to noise ratio, right? So this is signal to noise and distortion ratio. So there are two different terms. One is noise and one is distortion. So distortion is related to the harmonics, whereas noise is something which is not wanted in the signal, right? So what synad basically, how is synad calculated is you take the power of the signal plus the power of the distortion and you divide it by the total power, which includes the power of signal plus the power of noise plus the power of the harmonics. Okay, so now let's look at these VIs through LabVIEW. Let's put them on LabVIEW and let's look at each of them. All right, so first look at frequency response. Okay, so let's say I have a filter, okay, and I give some input to the filter and I get a particular output from the filter. Now, based upon this information, I want to get the frequency response, right? So we just seen this can be done using the frequency response VI that we have seen. So okay, let's see the block diagram of this. What I'm doing here is, so I create this is a filter. I give it a time domain signal. Okay, this is an IR. So I give it the time domain signal, and this is my main signal. Okay, this is my main input stimulus, and this is my response. Now, based upon this information, I feed this information to the frequency response VI. Okay. Now, the output I wired it to a frequency I wired it to a graph. So as you can see, when I run it, the graph that I get, this you see, this is the transfer function of the particular system. That is the IIR filter. Okay. Fine. Let's study the others now. Okay, let's look at the power spectral VI now. So the power spectral VI, as you know, it takes a time domain signal and the output is the power spectrum, as in the power spectrum, which basically means the power versus the frequency graph. So at each particular frequency, what is the power? So what I've done in this VI is I have a knob by which I can change the frequency, and I have a graph. The graph is wired to the output of the power spectrum VI, and let's run it. So I've currently put it to around 350 Hertz. Okay, around 400 Hertz. So I see a peak at 400, right? Which basically means, also currently the signal that I have is a sinusoidal signal. Hence you see a peak at 50 Hertz. Change it accordingly, the peak changes. But now let's say if I change, if I
webinar, Web Events Made Easy.
मेरा भी डिस्काउंट हो गया, चल हो गया। Same will be 2 times 20%.
Alright, we're very sorry, there was some technical problem, but I think due to which the connection was lost. I think we're back now. So I will start going back some 5 minutes, which I think where the connection got lost. So let me just start with this demo. I think the presentation was covered before that. Fine. So let's start with the demo. Okay. So what this demo is basically doing is we have recently in the previous slides we've seen the power spectrum VI, right? So I'm just showing you how to use that power spectrum VI and how does the output of that look, right? So I'm giving a time domain signal to the power spectrum VI that I'm simulating using this function simulate signal, and I am plotting the spectrum on a waveform graph. Now if I give, so currently I'm giving a sine wave, okay, a pure sine wave of a particular frequency. So obviously if I am giving a sine wave of a particular frequency with no noise, the output, the power spectrum of that input signal would show a peak at that particular frequency, right? So if I run this, I expect a peak to be around 550 Hertz. All right. So I see a peak around 550 Hertz, right? And at all of the frequencies, the amplitude is quite low compared to this, right? But if now let's change the signal from a sine wave to a square wave, right? As we talked before, a square is a combination of sine waves of various frequencies and amplitudes. So I would expect peaks at various frequencies and of varying magnitude. So let's run this. All right. So this is the power spectrum for a square wave, right? You can see at almost all frequencies, there is a significant component of the amplitude, and there is no clear peak as such, but around 550 Hertz, you can see a peak which is greater in magnitude as compared to other peaks, right? So this is the fundamental frequency, and all the other peaks that you see, they are the harmonics or the other frequencies that are also present, which make up this square wave. All right, so let's look at some other demos now. Fine. So now let's look at the main demo for today. So we have seen basically the aim of this webcast was to do a continuation from the last time. And last time we looked at various functions to do various functions related to sound, right? We explored the sound palette. So the aim was to, once you have acquired an audio signal, what processing that you can do in the frequency domain on that particular signal. So we'll just see that. So the demo that I'm giving today is on a simple guitar tuner, okay, which is a very common thing these days. We have, so the demo has been made using LabVIEW and using the functions that we have studied today. And I'll explain, first we'll see the demo and then we'll look at the block diagram. Okay, so let me just open that. Alright, so this is the front panel. Okay, so now let's run this and I will produce the notes that are present in the guitar and let's see if it works fine. Okay, so currently I'm Okay, so this, as you see, okay, let's now pressing, let's say F note. Okay, fine. So you see what this, let me talk about the logic of this. So what I'm doing here is, first thing, there is I'm playing a particular note and my microphone is capturing that. Now through that I am taking that sound signal into LabVIEW. That's the first thing that you have already seen how to do that in the previous webcast. The last time webcast was all about this. How do you acquire audio signals into LabVIEW? So the first part is I'm acquiring this signal. Now once I have this signal, what I'm basically interested is, so the people who are not very familiar, I'll just spend some time explaining you the concept behind a guitar tuner. So every note has a particular frequency. Okay, so all the notes that you see, all the notes A to G sharp, they have a particular frequency. Okay, a very specific frequency. Now, what I'm basically doing on a very bigger picture is that I'm taking a signal, an audio signal, I'm calculating the dominant frequency of that, the fundamental frequency present, and then I'm comparing it to see what note the frequency matches to. So since A has a particular frequency, it's a 27.5 Hertz, so if this frequency that I get is 27.5, then the LED corresponding to the A note is lit, and in the tone information, the just right is lit. But let's say if it is a bit more than 27.5, let's say it goes to 28.7. In that case, it's sharp, right? So the LED corresponding to sharp glows. So that's how, if I have a guitar and I want to tune it, I want to tune a particular string, let's say the E string. So by pressing this tuner will help me and guide me whether I'm going towards the correct frequency and whether I need to increase or decrease the frequency, tighten the string or loosen the string. Okay, so should we now let's see the block diagram for this. So I've already told you the main logic. The main logic is this, but I'll just tell you how it has been implemented. Fine. So I'll not discuss in detail these two sub-VIs that you see. So this sub-VI, here I'm configuring the VIs that will help me to acquire data into LabVIEW, and here I am reading the audio data into LabVIEW. Okay. Once I have the data, now this is related to today's webcast. We'll discuss this in detail. So once I have this raw data, I am giving it to this particular VI. Okay. Now this particular VI is the tone measurement VI that I have. Now this VI, I am the output. Now once I have this, the output is a cluster. Okay. So I want a particular information. It's a cluster of various frequencies that are there. So I extract a particular frequency, the dominant frequency, and at this point I have a detected frequency. Now once I have, this is a very simple thing, right? I have a VI which is present, that I give input as a raw signal, and the output is the detected frequency. Fine. Now the logic is, okay, and the logic is, now this sub VI, here I'm detecting what frequency